Okay, guys. So let's start with this review. So we're talking about the book Scale. We're slowly going through the book and covering different topics of the book. All right. So last time we were talking about basically this adventure, this intellectual journey that the author is going through. Is this idea that he started with. He's a physicist, and so he started with um, understanding, particle physics and things that were not animated. And then he had some kind of like a personal crisis where they closed down this project that he was supposed to be associated with. Um, he also started to confront the idea of death because he was relatively um, old in his life, and he wanted to understand it better. Why, for example, human beings live a certain number of years. About 100. Why not 10? For example, uh, smaller animals live much shorter life, or bigger animals live longer lives. So he, as a physicist, many times we approach things like this. We want to understand them intellectually. We want to find meaning, through math and physics. So there was this convergence of things, and I like it because it's very interesting because probably we had a crisis like that, all of us in our lives, that push us in certain directions. Maybe even the fact that we discovered Bitcoin was due to situations like this. In my case, I had a similar. I mentioned already. I had many similar parallels with his experience, his life experience. I also transitioned from physical sciences to more biological ones, in particular neuroscience. Also because of personal reasons, there were financial reasons, like they were closing down the physics program in my university, um, and also the financial crisis of 2008. But also, my dad died of ALS, and so I wanted to do something more applied, maybe to help people with neurological conditions. So it's interesting. There are a lot of parallels that are I can see in his life and my life. But basically, we were here where he was trying to um, find some answer to the main fundamental questions about death. He was asking himself, and going through the literature, talking to people in the field. How much do we know about why we age, um, why we die, how long different animals live? And surprisingly, he didn't find a lot of answer because this field seems underdeveloped in comparison with other fields of biology. Um, and then, he started to say, okay, if maybe they don't know, if the biologists don't know, maybe I can find out, right? That is actually pretty much very similar to, again, what many physicists will do. We are kind of pioneers of science, where we go in areas where other people have not explored yet, and then we apply our thinking, and mostly based on this idea that we can measure things, and that we can, by measuring and finding mathematical patterns, maybe we can find some meaning. First is always how. This is in fact what Galileo taught us, that before answering the question why, you should always answer how. Because if you don't know how can you even hope to answer the question why? So first, trying to answer the question how, and in particular, if you can do it with mathematics, with patterns, sometimes it's not possible because it's so complex, so difficult, that there is no a simple equation that you can write. But maybe there are other areas in even something complicated as biology, and maybe finance, Bitcoin, etc., where we can find patterns, right? Um, and then we can try to understand why later, once we understand how. And many times what happened though in physics, we answer one how, and then we want to answer other hows, and it's like a kind of never-ending story, and we never arrive to the point where we can answer the question why. But that maybe is part of the process. So maybe why is simply answering how at a deeper level, right? So if I go to a deeper level and I explain how, maybe that is the why, right? But yeah, it's open questions, right? This is why I left this big question mark. But so he also explained how he had some precedent, right, where other physicists would try to approach this topic of life in general. What is life? There is, in fact, a famous book that if you never read it, I recommend it to you. It's called "What Is Life" by Schrödinger. Schrödinger, you probably heard about him because of the Schrödinger cat, right? It is kind of a thought experiment that Schrödinger proposed. But he is like one of the most important contributor to quantum mechanics. He wrote this famous equation, the Schrödinger equation, that we use all the time to understand how subatomic particles behave. It's like the equivalent of the equation of motions of Newton, but for subatomic particles. And also the fact that physicists were essential in finding out what DNA is. It's all the work of physicists, actually. Um, and so he had this precedent, and it's very nice because, for example, for me, it was very inspiring. Then there was somebody like Jeffrey West. So Jeffrey West was my inspiration in trying to understand scaling in different areas, or like, for example, Bitcoin. It was very, very um, comforting that somebody before us did similar work, right? That we are not completely crazy in trying to understand life from a physical point of view. We are already famous physicists that try to do this, and it's not crazy to try to understand scaling in areas like humans, right? Human activity, because Jeffrey West has done all this work. So it's we want to always, we want to go to new fields, but we want also to know that other people tried, and that maybe they succeeded partially, or maybe they fail. So, but it's always an inspiration. But he mentioned also another book that is this book. This is more not a physicist. It's more like he was like a polymath. He was very interested in many different things, like a Renaissance man, right? It's very nice to find people like this that can apply their thinking in many different fields. This is one kind of a classical book. It's very cool because it's more like a higher level thinking about how objects grow, our physical, biological forms, like this beautiful, beautiful Nautilus shell. It looks almost like a mathematical equation. In fact, you can describe it by a mathematical equation. Um, and so he started to say it's important, in biology, maybe. So he has this sentence here. It's a kind of old-fashioned way of describing things, a little bit outdated language, but what he's trying to say, for example, that maybe we cannot understand by using math and physics. Uh, consciousness is not explained by my comprehension of all the nerve paths and neurons. By the way, modern science is actually trying to do that, right? That is the next step. Because first we are trying to understand how biology works, all the things like metabolism, right? So he's talking about these the laws of energy and all the property of matter and chemistry, all these things that are in the physical world. Uh, he's mentioning the soul. Modern science is getting away from the soul. We are, soul could be your personality, how you express yourself, all your memories, your tendencies, but it doesn't have to be something outside the body. And modern science is converging that to that understanding. Same thing with consciousness, where there are some people that are actually trying to understand mathematically consciousness. Actually, I worked in a laboratory with this Italian scientist, Giulio Tononi. In fact, when I joined neuroscience, it was mostly because I wanted to understand consciousness. This probably is the biggest question of all, even more than what is life, what is consciousness, right? That is the next level. And science is moving in that direction in trying to understand it through material things like nerve paths and neurons and connections and patterns, but we are not there yet, right? We are coming closer and closer. Or things like goodness, but even these things like somebody moral tendency, they are located somewhere in the brain. But he was leaving them as it's more difficult to understand them, or maybe we will never understand them. I don't think so. I think eventually we will understand all these things through science and using technology. But he was talking, say, okay, let's start with understanding something like the construction and growth and working of the body, right? So first, let's start with the simplest thing, even if they seem very complicated, how things grow, how they work, how they function, and maybe we will not be able to do it with things like consciousness, but at least we can try with the very simpler things. This is from the book, this book on growth and form. Like I say, I think eventually everything will be done that, but for sure we want to address this first. And so, and he was mentioning that the book has some limitations. It's an old-fashioned book, but imagine to us now seems kind of obvious, maybe to use things like physics and science. For some people, it's not obvious yet, but this was a long time ago when this book was written in the end of 1800s, and at that time was actually a big deal even to think these kind of things. People didn't think it was okay. It's okay to understand the planets and maybe what happened with heat and other things like that. By the way, even these things, right? In ancient time, people were thinking that we were angels pushing the planets around, and then little by little we started to think we were natural forces. And then when it was time to describe biology and using things like physics and science and so on, people resisted that idea. But so it says even if the book doesn't go in the details and it doesn't have equations and things like that, it was one of my inspirations. So it's a cool book that if you have a chance, you can even find free PDF, but the Kindle version is just $9. So it's one of a book that as you read this one, maybe you want also to consult and create like kind of a library to understand why things grow, right? And because it's kind of a theme that we're developing. We are trying to understand why Bitcoin is growing, because this is all what we do in this book club is in the end related to Bitcoin, because most of the people that are listening to these lectures, or discussions, whatever you want to call them, are interested in Bitcoin ultimately. And so we try to understand Bitcoin as almost like if it was a living organism, right? So for us, it's anything that help us to understand why things grow, it's useful. But anyway, so and he particularly say, well, in the book, in my search, because I remember one of the motivation for him to go to this field of biology was he wanted to understand why we age and die. But again, it's very similar to one of my strongest drives, but I want also to understand why we age and die. But in his approach, he wants to settle with that, right? Okay, I understand it, and then I'm not going to do anything about it. In my case, one of my dreams is actually to help in defeating aging, and that I develop a device, by the way, that helps with Alzheimer. It keeps your brain young. So I already made a contribution, but I hope to make more, so we can actually maybe even reverse aging one day. And one of the most important concept. So if you want to understand how something age and dies, of course you want to understand how it lives, right? How it functions. And he mentioned, this applies to animals, uh, machines, maybe company, even a civilization. How do they grow and how they die, right? Um, so, and what is very important in all these systems is the concept of energy, right? Considerations of energy, because energy is one of the most important ideas, right, that was developed. It's actually in physics was developed relatively late. I don't know if you know a little bit of history of physics. Like Newton didn't know anything about energy. The concept of energy was not developed by Newton. It was developed later, like in the 1700s. They were doing experiments. They were dropping like different size of balls in clay, because imagine at that time they didn't have a lot of complex instruments like we have right now, but they knew that there was something related to the motion of an object. So if you had an object was large and was moving, it will be more difficult to stop it, right? And a smaller object, and so they studied different size objects falling, and they could, if you had a clay on the ground, then you could see how far the object went into the clay if you dropped them from certain heights, right? We could do all kinds of experiments like that, and they develop little by little. They develop this idea of energy, and energy in physics, everything is calculated and has a very precise definition. We like to make very precise definition. So, but we can go back and see what physics says energy is. But is basically a quantity that is related to force. There are these forces of nature. So if there is a force and you're applying this force to some object that is moving, you need to apply a certain amount of force for a given distance. So remember, I told you that when we did this first experiment, we were dropping object at a certain height, and then we were seeing how deep they went. So if you took the force that resisted the object to go through the clay, so because the clay exercised a certain force on the object, if you multiply that by the distance that the object went through the clay, that is a measure of energy. But has much more implications in terms of how it's used in physics. It's one of these quantity that in certain condition is conserved. It's neither destroyed or created. In modern physics, we think actually matter is a form of energy. It's almost like crystallized energy that you can free and create energy from the destruction of mass, right? Or the other way around, where you can take energy and create particles, create mass. But most of that change between mass and energy involves nuclear forces. Most of the things that we experience on daily life, energy is kept more or less constant. Now it can go in the environment, it can be dissipated in the environment, but it's something else that we can discuss. But in terms of biology, energy is fundamental, right? Because this is what is trying to discuss here, the role of energy in life. And we know that it's fundamental, right? It's very important. And one of the reasons why, so first of all, let's say this, right? Because these are some of the things that maybe needs to be understood better in general. Most of the energy that we are dealing with is chemical, right? I don't know if it's obvious, but it should be, right? Because mostly we eat food, and then we go through this process that is very complicated. There's many steps. It's very humbling for a physicist to actually study these kind of things, because you learn to respect biologists. In one end, we think we are better than anybody else in science because we do all these very complicated equations and mathematics, etc. But then usually most of the things we study don't have all these many steps. Even when you look at some of the complicated chain reaction inside the stars, they have a relatively small step, but the difficulty is understanding the math behind them, how regular they are, and making sure the equations work, and that is where the complexity comes from. But in biology, there is all these different paths and different steps. It's very redundant. It's almost like one of these Goldberg machines, right, where to do one simple task you do 15 different tasks, right? And there are reasons for that. Evolution, right, build on things that were there before. It doesn't completely restructure the body from scratch. So if there is a pathway that was used in the past, and then you want to innovate, right, it's not conscious. It's all this process of evolution through natural selection. Many times the physiology will use something that was already there, right, from our ancestor, and then it builds on it, and it becomes very complicated, but it's still pretty efficient, right? So basically, we ingest food. The food has different bonds. It's kept. There are different substances, different chemicals that we can convert and free some of the energy that is stored in this food, and then use it for us. And the body is doing many different things with this energy, right? And it's very important, because anytime, and the book will go in more details, but as a general preview, the main idea is that most of the things in the universe tend from organized forms of energy, and one organized form of energy is something like, for example, kinetic energy, right? If you have a ball that is moving, that form of energy is very organized, because it's mostly in one single direction. You can describe it, right, using some equations. But then if it hits the ground, it diffuses this energy to many different particles, all the things that the atoms that form the ground, and these objects, these atoms starts to move in random ways, right? So you go from a very organized form of energy to something disorganized. And this disorganized form of energy, we call it heat. It's just a way of describing this random motion of many objects. In theory, every object moves in a very precise way, but because it's so disorganized and so random, it's very difficult to extract that energy to do useful things. You can, but it's always in an inefficient process. So the result of that is that over time, you get more and more disorganized energy. So that is the tendency to go from organized to disorganized. And to go back to any form of organized energy, like, for example, yes, you can take fuel in a car, you can burn it, and then you can make the car move in an organized fashion, organized form of energy. But there is always a loss. That process of going from disorganized to organized is never 100% efficient. So the overall disorganization of the universe is increasing. That is kind of, one of the riddles of the universe. Why is like that? And if we have a civilization, let's say one day we have a civilization that has survived millions of years, maybe even billions of years, and at a certain point we will have to deal. That will be the most important issue. Right now we don't care, because we dump heat in the environment, and it's not something that we are worried about. But one day some advanced civilization will have to deal with the fact that the entire universe is a big pile of disorganized energy, and I don't know, right? That will be the big question of that time. But right now, until we have enough space to dump heat in the universe. Right now, we mostly dump it in the world. We don't even care about the universe itself. Uh, it's okay for us, right? Because we are trying to create organization and order inside the body. And to do that, you need energy. So that is actually, if you want to look at a very, very high level, why we do need energy in life is because life is all about being organized, doing all these very complicated processes, right, that require information and uh, body needs to know, through the DNA, okay, I need to put these proteins together. I can build this tissue, all these things, processing information in our brain. All these activities require energy because you're going from disorder to order. And that is allowed. The universe can do that, but you have to pay basically almost like a currency. Like you have to pay a coin, and that coin is energy. So I don't know if you ever thought in that way, but that is one of the reasons why uh, living beings need energy, because they are creating locally order and organization, and that requires energy to do that. And the byproduct of that, you see, this is what they show. First of all, we call this process of transforming the food into useful energy, we call it metabolism. So these, see, they call it body energy currency, right? And then we dump heat because it's unavoidable. If you create order in one region of a universe, that is your body, then you have always to dump heat outside. And that dumping is done through the heat, right? We produce heat. If you look at the human body through infrared camera, you see how we glow. We continuously glow, even when we sleep, etc. We produce this heat and we dump it in the world. But in doing that, yes, we increase the order inside us, but we made the overall disorder of the universe bigger. And also there are other type of ways, right? We carbon dioxide, water, and all the other byproduct of metabolism. So that is what happens. Um, so he mentioned this and said, all the things that we do, from the firing of neurons to building proteins that allow to build the different type of tissue, repair, also the energy that we need to move or do things, right? If we lift something, we need to get energy from somewhere. All these things are the product of metabolism. We need to produce energy, or get energy from somewhere. Um, and and so, from a physicist point of view, then this is actually perfect because it's a very well defined quantity. This idea of energy in the body, we can measure how much food we intake, and there are ways of calculating how much energy there is in the food. You can, I don't know all the details, but we can figure it out. We can search it. Mostly, from what I understand, they burn a food. They literally burn it, and then they allow it to burn it, and then they see how much heat is released, right, from burning it, basically. And then you can say, okay, this bread contains such and such calories. And it's a little confusing because it would be nice if in many different fields, everybody use the same units. And in physics, we are very strong in trying to do that. But then sometimes for historical reasons or other, maybe because it's more convenient to use um, this quantity. But for example, in biology, and whenever people talk about food, etc., right, they use these calories, but it can be converted in the quantity that we like in physics. In physics, we name units after scientists. That is something that is very common. They deserve it. So, for example, Jules, he was one of the people that started to study the idea of energy, in particular how to convert kinetic energy into heat. So he will have experiments where it's very cool. Actually, we did some of these experiments in our physics classes. You can take a container, you put water in it, and then you will have like little paddles that steer the water, and then there is some kind of a gear or whatever, and you keep it almost like a thermostat, right? So there is no water heat leaked in the environment. Then you will wrap around a rope, because remember, a lot of these experiments were done in a relatively primitive way. People didn't have all the sophisticated things we have right now, all of these electronics, all these very sophisticated tools, but they were very ingenious. So Jules did experiments where he will have, like, imagine like almost like a cylinder attached to many different little paddles that will steer the water if you turn it around. Then this wheel was attached to a rope, and then he had a weight, and he will release the weight, so you could convert, right, the gravitational energy into motion of a paddle, and then measure the temperature of the water, and calculate this conversion, right, between one form of energy to another. So he was one of the pioneers in trying to understand what energy is, that you can convert one type of energy to another. So they named the unit of energy with using his name. It's called joules. And you can convert calories. See, there was a time when I was teaching that I had all these numbers in my head, but you can check it out. You cannot, in fact, we can do it together. How many joules is a calorie, right? Because everybody's familiar with this word calorie. Is a calorie. I remember it by heart at a certain point. Yeah, so 1 kilocalorie, that is 1,000 calories, is equal to 4,000 joules. So that is the type of conversion. But you can always go from one quantity to another. So you can calculate how many. Basically, they say 90 watts, right? So this is how it works. If you're interested, watts will be. It's called actually a power. It's not really energy. It's a measure of power. So energy per time is called power, or energy rate, and is measured by another scientist named called Watts. He was a Scottish guy, and this Scottish guy studied steam engines, because steam engines were the most important invention of that time, right, in the 1800s. They had practical uses. They could make trains and actually give energy to things like machines that they could do fabrics. It was very important because people were making fabrics by hands for century and century, and so clothes were very expensive. Then all these people, mostly, see, it's actually interesting how the names change, right, according to the country that was kind of the most powerful country at that time. It's kind of curious, right? Because science is open to everybody, but of course, historically, the center of activity is always where that superpower was operating at that particular time, right? Like Galileo, like during the Renaissance, Italy was the center of the world, in a sense, right? We were the most advanced country at that time. During the Renaissance, we had all this innovation, and Galileo lived kind of an end of a Renaissance. This is why when science was born, Galileo was one of the main contributors. I don't think there is a unit named after him. There is one named after one of his students, it is Torricelli, and but not after Galileo. But science went from one country to another. Newton, right? And then Jules, he was French. France was one of the center of the world, and then we went to England and Scotland, right, where it was the Industrial Revolution. So not by chance when people started to understand, because we wanted to understand, right? This I put so much coal in this steam engine, how much energy per second I'm going to get, right? So if I want to make machines, I want to make a practical application, I want to understand the theory, but then I want to see how to apply, right? So Jules is energy per second. So it's an energy rate. It's how much energy you consume per second. And the idea of this 2000, we could do it together if you like. We can. I can show you how to do it if you're interested. But the idea, right? 2000 food. What do they mean here? It's the total calories that you consume per day. So it will go like this, right? So we can try to do it together if you like. How will you know why these two things are related? They say we consume 90 watts, right? It is crazy. First of all, think about that, how crazy that is. Watts, 90 watts is like the energy consumption of a bulb. So we are like a little bulb, right? That is absurd, right? Like all the energy that you consume is like the same one. But this shows how efficient we are, because imagine having something like that does all the things we do, even a robot, right? If we had a robot that needs to do all the things that we do, even like ChatGPT uses an enormous quantity of energy to do the things it does. That is one of the advantages we have relatively to this AI or even robots. We are super efficient. Evolution was able to do so much with so little. So how will it go, right? So basically it's energy consumption. So you will take joules per second, that is 90, and then you will multiply by the number of seconds in a day. So how will you do that? You will take 24. I'm doing this with a calculator. If you want, you can do that with me. So I'm taking 90 and multiply by 24 and multiply that by 60, and then multiply by 60 because there are 24 hours, 60 minutes in 24 hours and 60 seconds. So 24 times 60 times 60, and then you multiply by 90. That will be the total number of joules that you consume in a day. Okay, so that you need to survive. It's some 7,776,000, something like that. So that will be the total, right? And then we want to convert it in calories, and because we want to see, because that everybody knows, right? They say, oh, you need about 2,000 calories per day for a man, for example. So this will be joules, and remember we say the conversion is for 1 kilo, right? That will be 1,000 joules. How was it for 1,000? Let's go back. Let's check. It says, in fact, I have this thing here. I have on a website. I just say how many joules is a calorie, right? And so we can go the other way around because this thing is converted. Okay. So let me write down the number. 7,000. What did we do? 7 million. I got 7,700,000, something like that. 7,700,000. So I need 30. Yeah. So when I do that, I get 1,857. So 1,800. Okay, not too many zeros. 1,857 calories, right? This is what I get. Because, yes. So this is the conversion, right? So 2,000 calories. It's what you will consume over a day if you do 90 watts of, if you need to 90 watts of power, right? Or joules per second. So you can do that conversion easily. It's really cool, right? That we can go from one thing to another. Okay. And they say, the book says it's, we have all these things that are, and here I try to show how, for a physicist, if you approach this from a physics point of view, but doctors do the same, but the idea of a physicist will see, I want to measure everything. I want to measure how much energy comes in. I want to measure the blood pressure. I want to measure the brain waves. This is what actually I was doing when I was playing as a neuroscientist. I was trying to understand these brain waves, and they are physical units. You measure them in volts. It's like a battery, right? We are producing this voltage, and you can measure it, and you can measure the changes in voltage. They are very small, like when you measure it on the surface of a skull, they are like 1 millionth of a volt, so very, very small. They are bigger inside the brain. They are so small because they go through the skull when you measure it with what is called the electroencephalogram. They go down by a factor of 1,000 when you measure it outside of the brain. Inside the brain, they are more like thousands of a volt. But it's like a little mini battery, right? 1,000th of a volt. And so you want to measure pressure. You want to use different kind of signals, like how fast the heart beats. It's actually quite cool for a physicist to play with all different measures, all things that you can measure, and then you can look at the relationship, right? Is there a relationship between this quantity and this other quantity, temperature and this other one? It's a very interesting playground. It's very complicated data relatively to what we are used in physics. But that is the idea, right? We would like to measure everything and find patterns and see. And what Jeffrey is telling us, that there are all these different quantities, right? That the body settles on, like, for example, why the heart is beating once per second. That most people will not think about that, but the physicists will ask that question, say, how come it's once per second? Why is no higher? Why is no slower? Why we settle on that value, relatively to other values? It's really cool, right? It's a different way of thinking about the world. We want to measure everything. And his idea is, okay, let's focus. There are all these numbers, and they seem, somehow arbitrary, but let's focus on this energy itself, right? Why 90 watts? Where that number comes from, right? Because it's kind of almost like our territory. Energy is very much a physics quantity more than other ones. And why this complicated organism that does all these different things settled on this amount of energy. And one of the things you want to do when you study these things is not just to focus, sorry for that, not just to focus on one single individual, but maybe compare many different ones, right? Because if you can compare many different, not just individuals inside the same species, but maybe different species. So if you want to try to find a pattern, maybe you want to say, let me compare it with many different animals, right? I have different animals around in the world. I'm going to look at bigger animals than humans, smaller animals than humans, and then see if there is a particular pattern in maybe size. That will be an obvious thing to compare, size and the amount of energy that the animals consumes. And such a pattern has been found. And in fact, it was not a physicist who found it. It was a physiologist. So kudos. And his name is Kleiber. And he's from Denmark. And he did this. He published actually this, he says, in obscure. I will actually, at a certain point, would like to find the original paper. Sometimes it's really cool to go back and find the original paper, that somebody published like a world-changing result. I had at a certain point, I had actually bought a book that collected all these articles, because sometimes it's difficult, like even with the internet, maybe, and we can look it up, right? Maybe if we can find it. And if you guys find it, put it in the comment. I would like to see that article. Maybe it's written, I don't know if it was written in English or if it is written in Danish. So it was really this cool book. If I found the book, I will put it in the comment or somewhere in the notes. By the way, you can find these notes in my Patreon. I put it in the video a link where you can go and find the notes. I will update them on a continuous basis. And if you are part of my Discord group, you get these notes for free. So there be bibliography, there be graphs, notes, and all kind of things like that. And if I found the original article, maybe a link, I will post it. And if any of you is Danish and is written in Danish, and if you translate it, that is really nice, because I will be curious to read the original paper. But he found this relationship, right? This was all the way in the theory, but people probably started to understand that there was some kind of a pattern, right? But the beauty of what Kleiber did was to do it in a very precise manner. Now, all the details of how I did it, I would like to also understand it. And this is why it would be interesting to read the paper. But again, you can measure metabolism of an animal. First of all, you can just see how much food they consume, and then you can calculate, like we say, a different way of calculating how much energy there is in a food by burning it or doing other experiments that scientists do, to know how much energy there is involved. So in theory, you could see, okay, this animal is eating this, maybe even just supply a little bit more food, less food, see if he loses weight. But they do it in a more direct way, where they actually look at how much carbon dioxide is produced, like by measuring the waste, right? You can actually derive, if you know something about the metabolism, you can derive about how much energy they consume. I don't know all the details. It's today you can just do a very quick search and find out how these things are done. But there are ways of measuring the metabolism of the animal, and the mass of the animal is relatively simple. And why will you do mass versus the size? You could also do the size, but mass is probably a better measure, because it's a measure of how many cells there are, right? So if you double the size of an animal, because we have this joke in physics, we call it, I should actually put it, maybe next time I will put the joke. We have this joke of a spherical cow. We say in physics all the time, let's assume we have a spherical cow, right? And it's an internal joke, because basically we're trying to simplify the problem. A cow is not a sphere, right? It's complicated. It has a weird shape and has legs and a head. It's a much more complicated geometrical shape. But for rough calculations, you can always assume it is some kind of uniform volume, right? Like a cube or a sphere. So it's the physics cow, the spherical cow. And so, the volume of an animal should be proportional to how many cells there are there, right? Because you double the size to make the animal, assuming, because it's very interesting, right? Even if you go through, so in particular, if you focus on mammals, right? But then once you go to other creatures like birds, reptiles, they start to be a little bit different. But in general, how biology expresses itself, right? At least the higher form of life, it's similar, right? Like, for example, the neurons in the brain, you know that there are no rat neuron. Now, of course, if you go inside and they look at the DNA of the cells, yes, that is different. But the shape of a neuron, the ability of a neuron to produce signals, they are very similar. The neurons of a rat and the neurons of a human, there are a lot of similarity. They are not very different. There are no larger neurons for the humans. They are all kind of the same size, the same capabilities, and so on. It's just that how they are used, the complication of the networks, etc. Same thing with physiology. Yes, they can change a little bit in terms of some of the things we can do versus some of the things that the animal can do, but the type of physiology is very similar. The density of the tissues, how many cells are in the tissue, the type of tissues. This is why we can do experiments on rats, at least initially, and test some of the drugs that we use and kind of assume that something similar will happen to humans. Now, at a certain point, there are similarities, there are differences, so you will have to be careful. But, this is why we always test things on first in animals, then we always test on humans too, once we know that the drug has some chance to be useful or it's not too poisoning. But the point is that there are a lot of similarity in physiology, right? What changes is the mass. So if I make the mass 2 times bigger, I'm expecting, because of the same type of density of cells and so on, to see 2 times the amount of cells, right? That is at least an initial assumption that I could make. And so mass is a good quantity to look at. And the idea is there are all these different animals. They are so different, right? I could initially, let's say that I wanted to do this experiment like he did, and imagine it was a real experiment. So this is why I need to dig more. I want to understand more the history. Such an important example that we mention it all the time, that I want to learn more, maybe even learn more about Kleiber. I didn't do yet. I will dig in maybe for the next meeting. Who was this Kleiber, right? And we know that he was Danish. He was working in the 30s. But what made him do this, right? Did he have some thinking behind that? Did he do it where it was actually him going, checking all these animals and doing the experiment? I don't know. I want to know more. And he was measuring all these quantities. How did he do it? And so on. But the bottom line, though, behind, it's always interesting. I'm fascinated by history of science, is that he found this pattern, right? So he was measuring directly or indirectly, maybe going to the literature and putting together all the data, because sometimes you can do that. You don't have to measure it yourself. Of course, it's much better that you do it yourself. Sometimes the literature can be wrong, but you also can collect data. Nowadays, there are a lot of catalogs. There are all kinds of different things that we have more data that actually people use. There are like many catalogs of, in particular in astronomy, etc. We are sitting there with all this data, and nobody is analyzing them because we are overwhelmed by data. But so if you take the mass, right, I'm measuring the mass in kilograms. I have very small little animals like the mouse, and I have huge big animals like an elephant. Then I measure how much energy per second, right? This watts quantity that is basically it's called power in physics, but here they also call it metabolic rate, right? Because we could convert it in calories. So we use like a physics unit, but it could be also calorie. But here, in this other graph, they use calorie. But you can convert one to the other. Calorie is more like a biological quantity that people use. And in the beginning, you could say, maybe I do it only with mammals, because I think there is more uniformity, right, in mammals. But you see, in this graph, for example, we introduce birds, right? So we have birds and cock, goose, and small birds here. And so they start to introduce different birds. But in this graph, look what they did. They actually extended this relationship that initially they found in mammals. They started to extend it into things that are not mammals, like amphibians and reptiles and even insects. That is crazy. And then they started to extend it even to unicellular organisms. Right? It is kind of absurd. And notice, of course, there are similarities and differences, and we can discuss them. One of the similarities, you can see all these slopes of these lines are similar. What is different is the y-intercept, right? It seems that there is like a shift to go from here to there. And in fact, right, it's almost a way of identifying the animals. You could even say, like, maybe this divisions between animals that we have, they are mostly based on like external factors, at least in the beginning. Now we have all these more sophisticated tests in terms of DNA and all kind of things like that. But this could have been an early way of distinguishing between the animals, right? It depends where do you belong? Do you belong along this line or this line or this line? And then you can kind of classify different type of animals in terms of this relationship. Now, and we can, we will spend more time understanding all these because this is such a fundamental example of power law, right? Because the book Scale, it's discussing this property that they say all the time, that is so fundamental: scale invariance, scale invariance. If you read the book, if you follow my presentations, little by little, this idea of scale will click, right? Because it's the entire purpose of this book, telling you how important, fundamental this idea of scaling is. Look at this. By understanding scaling in the animal kingdom, we understand something fundamental. We are finding a very fundamental pattern, because this is what we are trying to do, right? We are trying to see if through the complexity of life and metabolism, Jeffrey make a big point about it's probably one of the most complex mechanisms inside the body. Go and pick up a biology book. Maybe next time I will show you a diagram. They have all these very, very complicated diagram of all the different pathways, all the different steps, because it's not like in a steam engine. A steam engine, you take a bunch of coal, you turn it on, it produces heat. Now there are some stuff happening inside the core, right? There are reactions with oxygen, etc. But in comparison, it's very simple. What happens. In the ancient time, we were thinking that maybe heat was a kind of a fluid. We had all kind of crazy theories about what heat is. Nowadays, we know what it is. It's just the molecules are moving faster. So when you have a flame, you have all these molecules of oxygen and carbon dioxide all moving very fast, and they collide with the container where the water is, and they transfer heat to the water. Then the water becomes steam and so on. It's complicated, in the sense that if you want to understand all the steps and how the energy is transferred, etc., you can spend quite a bit of time in understanding that. But in comparison with what happens inside the body and all the pathways involved, it's completely crazy, complicated. And biologists, and people that study medicine, etc., they spend a lot of time to read and understand all these complicated parts, and though even if it is so complicated, then it organizes itself and expresses itself in the end as the end result, right? Two simple quantity that you can measure directly in this very organized fashion. And that is also, if you're thinking about what people say about Bitcoin, they say, oh, you cannot have this beautiful, they don't call it beautiful. I call it beautiful, because if you say that, probably you don't find it beautiful. Because if you find it beautiful, you are already on the right path, right? You understand it. Why you call it beautiful? Because all these ideas, right, that you go from something so complicated and difficult to understand to something that is simple. Because even if you think of it, maybe a power law is not a simple thing. It's one of the simplest possible relationship between data, the two quantities, and all this complexity, all these interactions between buying and selling Bitcoin, ETFs and nations and laws and high and lows, and all these things that are happening in the world that could push the price up and down. It expresses itself in a power law over this long range. And it's the same idea here. And people resist it and say, no, it's too complicated. There are too many things. How many times people tell me that? All the time. And they don't realize that there are exactly examples like that where things are super complicated, like in metabolism. over many different animals. So it's not the metabolism of only one animal, the metabolism through all the different animals that are very different, that have different diets. Some of these animals are carnivores. Some of them are domesticated, like cows, for example. Some are them wild. So imagine the different type of diets that we have, right? And um, carnivore versus an herbivore, uh, domesticated animal towards relatively to a wild one, birds relatively to mammals, and though over all this incredible range of lifestyles, body mass, type of food, there is order and a precise pattern, right? So everybody that says that, oh, it's too complicated, too many things, etc. Well, we have this example as why your intuition, because our intuition sometimes can be wrong, right? Our intuition will say it's so complicated, there are all these things coming together. There is not a pattern. If I draw a graph like that, I could see like maybe a blob, right? There is a blob, or maybe with something strange, some kind of complicated curve or whatever, or maybe no pattern at all. And instead, there is a very, very precise pattern. Now, inside, if you look at every single dot, they don't fall exactly on that line, right? If I did this with planets, and at a certain point we can look at the planet because it has been mentioned, but one day I want to give you the data. We can go and collect the data and we can do it together and show you how beautiful the data from the planets is, how it forms a nice, beautiful power law. We can get the data and we can analyze it together. But in this case, there is a little bit more disorganization that you will see than if you were looking at planet. With planet is almost scary. Even there it is a little bit more complicated because the orbits are not exactly circular. There are ellipses when the planets influence each other. So if you really zoomed in, you will find some little deviation from that very precise power law. But because in nature, nothing is perfectly like triangles, spheres. Nothing is ever perfectly like a perfect objects of mathematics that we examine on paper, right? That are abstraction and idealizations. So you can see here when you go from something that is completely physical, like the planet, to something that is more biological, where there is more complexity, more variation in terms of lifestyles and different ways that the animal, because maybe a certain animal is more efficient than another in using energy. Look, even between woman and man, you see how women are more efficient in using energy because they are lower relatively to this line than men. Men consume more energy given their if you look at the same way, usually we are a little bit heavier, right? Because this is why we are shifted to the right relative to women. These are averages, right? So if you take the average woman, she will be a little bit um, less weight than a man, right? And in general, because she's lower than the straight line, it means that she's more efficient. If you are lower, you're a little bit more efficient in using energy. We are less efficient, maybe because for men, it's more important to have a lot of energy output because of the things we do. Like remember, our physiology is based on what we were doing when we were running on the savannah, hunting and doing all kind of crazy stuff. We are not evolved yet physiologically to keep up with our modern lives. And so you can look at different animals. Like, for example, look at these. Small birds are here. This means that they use, given a certain weight, so you can take a mouse and a bird with the same weight. The mouse will use less energy relatively to that weight. And the reason is this. You can even think, like maybe anybody wants to comment. Why do you think that birds need to use more energy? Anybody wants to comment make a comment? Let me know. is because of flight, right? Because they are flying, and so they use more energy because of flight, and and so for them, it's not a question of optimizing this energy consumption, because here is a question of trying to optimize how much energy the animal is consuming relatively to its weight, right? You want to stay on that line, and if possible, actually below the line. There is a very general pattern that almost all the animals follow, but in general, you want to stay as close as possible to that line, because that is what nature found to be kind of an optimization path, given the physiology of most animals. But there are times where, for whatever reason, because how the animal evolved, where the animal maybe breaks away a little bit, right? It cannot break too much, because it still has to do with limitation of how the physiology works, etc., the laws of physics or whatever. But in some animals, there is a trade-off. Like, for example, with these birds, the fact that they are higher in energy means that they decided that they want to use more energy given their weight. So basically, they need also to eat more, maybe, or maybe they need to be lightweight. They need to find different things to deal with this. But the reason that they need to use more energy is because of flight. So they are flying, and they decided that it's worthwhile to consume a little bit more energy, because flying gives you different advantages. You can escape from predators, you can maybe access prey in a certain way, but you will not be able to access it if you didn't fly. So it's a price that they pay in making less efficient in this uh, relationship between weight and energy. And so they are a little bit away from that straight line, right? So you actually can learn a lot and make sense of a lot of things that are happening in physiology. Like, for example, why the marmot is so far away, I don't know, right? But this is how you can approach this. You can start to look at this graph and learn all kind of different interesting things, and ask all kind of interesting questions, like why the marmot is over there. It seems that it's very efficient in terms of the energy consumption. And we can find out, right? We can maybe learn something about the marmot, why. But actually, this will be my. I'm curious now, why such a big deviation? What is all going on with that animal? Does it go maybe in? Does it go in the hibernation a lot or whatever? So it will be interesting to find out what is going on. Now, notice how birds like the ant they don't fly a lot. Uh, they are there. They don't have a trade-off, so they actually are basically like land animals for all purposes, and so they land almost perfectly on the straight line. The goose is a little bit higher, right? Notice I saw something in this interesting before. The condor. The condor is a little bit lower. Probably, right? What the condors do? They spread their wings, and they don't use much their wings, and so they don't consume much energy, because they follow the currents in the sky, and so allows them to preserve energy in that way. So there are many interesting things. The elephant, for example, he doesn't care. He says, I'm going to use a little bit more energy, maybe because they are big and they need to put down trees and do other things. So they use a little bit more energy than this relationship says it should use. But again, they are pretty much all along this line. So, and then, we go through the other type of animals, when there are big shifts in terms of energy consumption, like mammals for sure. In general, they are, their blood is hot, right? It's warm in comparison with these animals that are cold-blooded. So maybe this shift could be described by that, right? By the fact that they use heat in a different way. But we can explore this, right? We want to keep this meeting around 1 hour. So it's just the beginning of our exploration of the Kleiber's law. We can go deeper. Probably we will have one or two of these meetings discussing the Kleiber's law, because it's such an important law. It's very interesting. Is what, like, one of these first power laws that we are going in depth, and understanding it kind of gives us the key to understand power laws in general. And why, again, let's remind why is a power law. It's a power law because we are taking the log of a x-axis, right? And we are taking the log of a y-axis. And if you are familiar with the things that I talk about, right, all my X post and my articles, when you do that, when you take the log of one quantity and the log of another, and they don't say here, right? They don't say, oh, I'm taking the log. Here they mention log scale, right? Different graphs. I took them these from the book has its own graph. I took these from the internet. There are many different versions. I like this one because it has all the animals in it, right? It's really cool. This one, it goes a little bit more in details of a different type of animals. So it's nice to look at different graphs, but it's the same graph, right? But here they see they make a point of mentioning log. They use calories instead of watts. Here they don't. They do it in an indirect way. The indirect way is, you see how they emphasize the scale, right? So anytime you change the order of magnitude, so we go from 0.01, 01, 1, 10, 100, 1,000, 10,000. So it's a way of saying we are emphasizing the scale here, right? So it's technically we are taking the log, and same thing here. See, 1, 10, 100,000. So they are focusing on these big, huge changes of scale. For scale, we mean these changes of order of magnitude, and is also called a scale, the scale. Here, they do it in a slightly different way. They use the scientific notation. Many people, when I make my graph, they say, why don't you use normal numbers? And they mean things like that, 1, 10, 100,000, because they don't like the scientific notation. But really, the scientific notation, it's created exactly for this purpose. It was created by scientists to compare different scales, right? You see here, it's basically, I'm emphasizing the number of zeros. If the number is negative, it means we are having 1 over that number. So here will be a billion because, sorry, a trillion, because a billion is 10 to the 9, right? And trillion is 10 to the 12. So if it is negative, it means 1 over that number, or 0. Right, 11 zeros is always one zero less than the number expressed here, and then 1, right? So it will be 0, 11 zeros, then 1. So that a very, 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 very small number, that is the number of calories that, like, this very small unicellular organism are consuming, and their mass is also similar, right? 1 trillion of a gram. This is grams. Gram is already 1,000 of a kilogram, right? That is in Europe is what they use, right? It's similar to pound, right? What is that? Like 2 pounds is 1 kilo, something close to that, 2.2. But it's very familiar to European, because this is what we use in Europe, kilograms, and 1,000 of a kilogram is a gram, because kilo means 1,000, right? And you see how they use the scientific notation. So 10 to the 3 in this case will be 1,000, 10 to the 6 will be 1,000,000, because it's the number of zeros. And people sometimes complain about this notation, but actually it's a useful notation because it emphasizes the scale. It tells you how many zeros there are. So it's actually something that I will invite people to get used to it, because it's not very difficult, right? You can learn, and it's part of the idea of, that we want to learn something, new ideas, new skills. So it's not very difficult to pick up this scientific notation. It's a skill, right? Just think about the number of zeros that you're getting that number. So this will be a billion that has 9 zeros, right? And so on. And so different ways of showing the same thing. But the bottom line is that you are taking the log of the energy consumption, the log of the mass. And if you see a straight line, and it's not a perfect straight line because there is some little deviation, but there's an overall trend that can be described by a straight line. And the straight line is now drawn by hand. There is a procedure called regression analysis that is trying to find the line that goes through the point and minimizes the distance of each single point. And what that procedure gives you, it's the slope, and it gives you the y-intercept, because every time you identify a line, you need two numbers. You need the slope of a line, and you need the y-intercept, where basically this line meets the y-axis. The y-axis is where this quantity is zero, right? So where it intercepts that quantity, now there is not an animal that has zero mass, but you can always extend this line until you find that line where there is the y-axis, where the y-axis starts. That is the y-intercept. And then you can draw this line, or the computer can do it for you, right? Of course, these ones will have similar slope, but different y-intercepts, because you see if you extend them, they will intercept the y-axis at different places. But we can go, one thing we can do, then I can post the data on Patreon. You can download it. I want to see if there is a better place where maybe I can put all this material, this study material, because let's see if I can find this physiological data, because it will be really cool to ask ChatGPT to do this for us, right? Because it doesn't find the data, at least yet. Maybe one day it will be able to find the data for you. But if you give it data, like for example, in an Excel file, then it can do the regression. So I can show you how to do that. Wait, let me see if I can find the metabolic rate, because maybe somewhere there is like a database that I can look up, because it will be nice, right? We want to verify and not trust anything. So it will be nice if at least once in our life, even for me, we can reproduce this graph, right? And asking ChatGPT is okay, because many times it can show you the code, how to do it, and then you give it the data, it fits the data. It's not exactly you doing it, but using the tool, right? So going through the process and see if it actually is true. It's very different than just looking at the graph, even if you use ChatGPT. So we can do that next time, and then I can share the data and you guys can try to reproduce it yourself, because it's really cool to see actually this graph in action when you produce it. It is really, really nice. And then, basically it's this idea of logs, around the log of one quantity or the log of the other. And we can go a little bit deeper in the math of the logs next time, and show you how the main question which we want to understand is, given that we have a log relationship between these two quantities, why do we get a straight line, right? How do we go from an expression that connects the logs to a straight line, and vice versa? And then how we get the power laws, because power laws are a relationship where you have y equal one quantity to some kind of a power, right? But we can go through the math of all that. And the book doesn't dwell in these things because it tries to keep things simple and show you the idea and all the details. But part of what I want to do here, because we can take longer time, we can go a little bit deeper, and also because I want you to understand it and apply to Bitcoin, we can look at also the math, the simple math. It's all math that if you survive high school, at least you can refresh it. So next time, just as a preview, we can go a little bit deeper. Let me see if I can find the data. Maybe you can ask ChatGPT. We can do it together. I can show you how to prompt it to analyze the data, and then I can share the data with you, where if you are interested and you want to reproduce this graph yourself, you can do it. And then we can look a little bit of the math. Why, if we have a relationship like this, it should be a straight line. How the power law that is expressed as some quantity to the power of another, what that has anything to do with a straight line, because it doesn't look like a straight line, right? but it does, right, when you go from logs to linear and vice versa. And so we can go a little bit deeper into that. I'm going to see if anybody has any question at all. If it does, if you don't, I will stop here. Okay. Okay. All right. Then see you soon.